Hello everyone, welcome back to OnPrep, and today we are discussing one of the important system design interview concept, which is metrics monitoring and alerting system. This is one of the most widely asked topic in the system design interview, and this is another addition to my video playlist on system design interview on software engineers targeting for a role for staff software engineer to principal software engineer. And as we know, the typical time duration for this interview is around 45 minutes to 60 minutes. If you have not watched my step by step approach on system design interview, I would highly recommend for you to watch that video. It will help you to understand the step by step approach. It will help you to understand the format of the system design interview and how you can go over in a step by step approach, considering the time on each of the step you should spend. Let's start with step 1, which is understanding the core functionalities of the system. This is a infrastructure related problem statement where we do not have a user facing interfaces. So our main focus would be on the core functionality, implementations, and a working solution end to end, and we go deep dive for scaling the system for thousands of, and we will less focus on the APIs and the schema design as we do not have the user facing interfaces. We would like to make sure that the internal implementation of the solutions work end to end while satisfying the core functionalities of the system. So what does this system does? Let's start with the core functionality of the system. Metrics monitoring system is something which we already discussed in our previous system design interviews as part of the operational excellency, where we wanted to monitor the performance of our system which we have designed. But specific to this discussion, we wanted to focus on the monitoring the performance of the servers. So you can imagine there are hundreds and thousands of servers. So you can imagine there are hundreds and thousands of servers hosted on an on-premises infrastructure on which services are deployed for serving the REST APIs or user request. But we do not want to focus on those services. We only want to focus on the performance of those servers, and resources belongs on those servers like CPU, RAM, disk, network. Now, why do we want to monitor the resources on those servers? The answer is we wanted to scale our infrastructure if, let's say, the servers are overly occupied serving some of the requests and the CPU utilizations and RAM is very high. So we can scale out the server by adding more servers into the infrastructure, or if the resources are underutilized and these servers are free, so we can scale in by removing the servers from the infrastructure, which will help to reduce the capital expenditures. This is about metrics monitoring on this infrastructure. Coming to alerting system, why do we need to alert the system in case of any server failure or if the CPU RAM threshold is reached? We wanted to send the notifications to the business team, developers, or support team so that the relevant stakeholders can act upon it on maintenance of this infrastructure. So let's start with the step 1, which is functional requirement of the system. Collect the data or events like CPU, RAM, available disk storage, etc. Once we have this information, then we wanted to store this information for displaying on the dashboard or creating the alerts. These are the core functionalities of the system that it must support. So we can collect these events for each of these servers hosted in the infrastructure, store these information in some storage, provide a dashboard for the stakeholders to look at the performance of these servers, and when there is a threshold reached for RAM CPU utilizations which needs the intervention from these stakeholders, we can create the alerts based on the rules defined by these users. So let me add the rules as well. Create, update the rules for these alerts. Considering the non-functional requirement of the system, as I always recommend to start talking about the latency and the cap theorem required for such a large system. So we need low latency on loading the dashboard. And about cap theorem, as we are having the distributed system, we need high availability over consistency for this dashboard. What does that mean is, what kind of dashboard it would be. Let's say this is the graph we are showing in the dashboard, and we are talking about the CPU utilization for a specific server. So the graph would look like this with respect to the time. So for the first second, we are having CPU utilization of, let's say, 10%, and on fifth second we will have a CPU utilization, let's say, of 20%. So this is a graph what we are showing in the dashboard, and we would like to prioritize availability for this graph over consistency. That means if there are any delays on showing the most recent information in this graph, it's okay to have some delay instead of not showing this graph at all. So we wanted to prioritize to show this graph as quick as possible, even if we wanted to compromise on having some delays of milliseconds on showing these matrix information into this graph. Talking about the read and write request into this system, let's say we are having thousands of servers on which we need to collect these metrics every. Now the frequency of these metrics collections depend upon us and how do we want it to propose to start with. Let's say for these thousands of servers collecting matrices every milliseconds. Now you can see this would be very high number if we are collecting, let's say, these three metrics like CPU, RAM and disk every millisecond on these thousands of server. Maybe you can get into the calculations, but that's not we wanted to focus on in the beginning. You need to have this clarification with the interviewer. If you wanted to calculate the number of reads and writes and how much data storage you would need for 5 years or next 10 years. To understand more on this, you can watch my previous videos on Book My Show, where I have talked in detail about number of requests for read write and how to calculate the storage you would need for next or 10 years. As I always suggest to check with the interviewer if you really need to do this calculation. Probably that would not be the focus of this interview, because at the end of the calculation you would understand that you need a distributed system, that your single instance of the server would not be able to serve the request within the given SLAs, and you would need to partition the data. For this kind of such a large system where either the data might not be able to fit into the single instance of the machine serving for next 10 years, or your read and write requests are so high that for a single instance of server would not be able to read or write within that given SLA. So at high level, we will talk about the cap theorem here if we need to partition the data, and the performance of the system by discussing the latency, and we move forward. So what kind of input data we have in our system? We have the events like CPU, RAM, and disk utilizations that we wanted to store in our system. So we can have name, like what is the name of this event. It could be a CPU or it could be RAM. What is the value at given time? Value we can represent in terms of percentage. So let's say we have 0.58, which would be the 58 percentage utilization. What is the source of this data? We can have the host name or the IP address of the server. And another important attribute is the timestamp. Now this timestamp we can represent in a form of a epoch: 4, 5, 6, 7, 8, 9, 2, 3. Spock is the number of milliseconds elapsed from 1st January 1970. Let me move this on the left. And the next step is the API design. To start with, we can begin with a simple get REST API, which is API for the dashboard, where we will have the search query like the name of the matrix which we are interested on and the time from and to, and the source. This is a simple get API for the search query in our dashboard, and you can understand that this is a pull based. So when the dashboard is launched, it will query to a service to load these metrics and display in a form of a graph. But we also need to talk about how this dashboard would be updated at real time. We can have the short polling or long polling APIs, or we can establish the web socket connections as well, which will keep the dashboard updated. But that would be too much in the beginning, and we can get into when we talk about in more detail in our deep dive. We also want to talk about the APIs for creating the alerts and how these alerts will be triggering when a specific threshold has been reached for CPU or RAM on a specific server. But let's park that as part of the deep dive and check with the interviewer if he or she is really interested to talk on all those areas in detail, right, as part of the API design or as part of the system design in deep dive. However, this is good to start with the system design approach, and let's get into our next step, which is a high level system design. In high level system design, let's start with something simple. Let's say we have servers which are emitting these metrics, or rather we are collecting these metrics like CPU, RAM, disk utilization. So let's say collector service, and we are storing this information in some relational database. As always, we are not making any choice in high level system design. It could be simple Postgres or MySQL database. So these metrics are being emitted and the service is saving into this database, and the dashboard would be able to query these database for loading the metrics in the graph. So we will have the dashboard, which is a UI that can query this database. So if you see here, how does this servers emitting these metrics and how does this service can capture these metrics so that it can save into the database. From here, we can start thinking about the push or pull mechanism. Either these servers can push these events to this service via some API, or these service can periodically call these servers to get these events. So I can give an example of Prometheus. If this is a Prometheus service which expects these servers, or in other cases services exposes an endpoint slash health, so that this Prometheus can periodically call that endpoint to fetch the health of these services. So this is a pull mechanism which Prometheus follows. In case of AWS CloudWatch, which exposes an endpoint to the clients, so client can push health events to the Amazon CloudWatch. So this is a push mechanism. So from here we can start something, build our own system and explain the trade-off between push versus pull mechanism with pros and cons. However, as such, either of these works until we are good with these concepts and examples. In the case of servers, how does this push or pull mechanism would work? For that reason, we would need to have some kind of a services running in these servers which can either push or pull these events to our collector service. So let's say we have a service called agent which is running in these servers in the background all the time, which should help us to either push or pull these events to our collector service. So these agents are having a control over these servers. So these events can get these metrics like the CPU, RAM or disk utilizations on these servers and can periodically call this collector service API to push this information, and this service will save this information to the database. From the dashboard, we can query based on these metrics and load the graphs in our dashboard in a representational format to know the performance or state of any specific servers or the collections of servers or the collection of metrics based on the date and time range. We also need the alerting feature, which is another core functionality of the system. So from the functional requirement, collecting the data, storing the information dashboard, creating the alerts and rules. So let's touch upon that as well. We need the alerting system, which could be a cron job to start with. Let's say this is a cron job which is periodically querying these database, and whenever it encountered that any specific server is down or threshold is being reached for the RAM or CPU utilization, it can call the notification service here to send the SMS, email or call, which we would not get into detail, but let me point it out here. We can create the alerts into the system, and based on these alert, this cron job would run. So we need the alert service as well to create the alert and the alert database that we get into detail when we go into deep dive. But as of now, if you would see that the basic end-to-end functionalities is working fine, right from capturing the events on these servers based on from these agents, storing this information in the database, loading into the dashboard, and triggering the alerts based on the events. But this is not a scalable system, though it satisfied all the core functionalities and we are able to explain the end-to-end flow. So let's get into the deep dive. Let me copy the basic flow diagram for the deep dive. In the deep dive, start thinking about the bottleneck in the system for making it scalable. So if we have hundreds and thousands of these servers, let me create some to understand the problem statement here. So we have these servers continuously sending the events. So it could be millions per second events sending to this single service, so that would be overloaded and would not be able to capture a single server of instance would not be able to capture all this information. These hundreds and thousands servers continuously sending these metrics to the single instance of this service, so it would not be able to handle the load. So now we have identified we would need to increase the load on these servers. Even if we scale these services to multiple instances, there is another issue what we see. Currently, we are following the synchronous communication that is not scalable for these kinds of write heavy system. So we need some kind of asynchronous or rather decoupling these services and database to handle such a write heavy load and scale individually and independently. So let's introduce a message broker in between. It could be managed service from the cloud and like SNS, SQS from AWS. Also a popular message broker which works based on the topic and queue, Kafka. Let me create some space here. So we need multiple instances of these services as well. And if we need a multiple instances of this service, we would need to have some kind of a load balancer. So let's introduce the load balancer here as well. These servers are sending these requests to this load balancer, and this load balancer would be sending the request to these instances, to these multiple instances of the service. These services is just publishing the message to the Kafka topic. Here we need the load balancer. Now you can see why I have not used the API gateway here, why I have used the load balancer. And that's the differences. That's the difference between load balancer and API gateway. So this is not a public facing servers. Probably this is wrapped under a virtual network here. So because this is a on premises infrastructure, we do not need uh, authorizations for these events or write heavy events. We don't, and we will also handle the rate limiting or aggregation from the customizations of these services. So we do not need the features of the API gateway, and we wanted to balance the load between these multiple services. That's why we are using a load balancer. Let me remove this back. Now we are able to write these metrics from all these services, and we decoupled using the Kafka. And Kafka now has all these metrics. We can scale the Kafka depending upon the load. We can partition the Kafka based on the matrix name, or based on the machines, or based on the host. Next is to consume these messages and save in the storage. For that, let's introduce the consumer for these Kafka messages and store in the database. And for sure, we don't need this relational DB because this is not tuned for write heavy. Also, this is not good for querying the large range. For that, we would need, so let's delete this and this, move this dashboard to the bottom right now. This service, this would be the consumer. This consumers would be the cluster group of cluster Kafka consumers, which is nothing but set of services consuming this Kafka messages and storing into a database. This database we need to talk about. This database should support the range query. So this is a database, and if we wanted to this database to support the range query, so let's include the query service. This query service can make the range query, like for a specific machine from so and so date and time. This database should be highly optimized to serve the large range queries that can be populated into this dashboard. So we can propose something like this should support the large range queries. So we can have a online analytics processing database, which is OLAP. Another is the OLTP, which is optimized for transaction. This database is optimized for the range queries. The examples are Snowflake database. We can propose the Snowflake database for this OLAP operations. These consumers are saving these messages to this OLAP database. Now we can also talk about sharding this database into the multiple servers, so that this consumer would be able to write into these database as it's a write heavy system. But let's take a step back and connect the dots from our requirement. These servers are, we are capturing the data every milliseconds from these servers, pushing to the Kafka. So far so good, but do we really need to store all these millisecond information in our OLAP database to serve for the dashboard query? Probably every millisecond information might be required for analytics purpose, for running the machine learning model, but we definitely do not need this granular level of information for our dashboard or alert system. So we can change this consumer to a aggregator service. What does this aggregator service can do is, it can aggregate the millisecond of data into a second. So we can convert this from, so that this database will have information at every second granularity level. For example, on 5th December 2024 at 9 a.m. on first second, the CPU utilization was 58 percentage. This is how this database can have the information at a granularity level of every second. Then the query service can query these database to load this information and populate in the dashboard. So far so good. But how about if we need the millisecond information for running our LLM models? We lost that information and it is not good. It is not the best practice to lose the information. We can get the millisecond level of information from the Kafka. So we can have the another service which can read these information from Kafka at a millisecond level and just dump it to any blob storage. We can introduce the blob storage which is cost optimized S3 as an example. So how does these data can go into our S3 bucket? So what kind of a service it could be? This service needs to continuously check in the Kafka if there are any messages and put into the blob storage. It could be simple lambda or it could also be a cron job here which can continuously check and push and just dump these raw data in our S3 bucket. Let me call this as raw data. Okay. So far, so good. This raw data can be used by the ML team for running the LLM model. And this is the real-time data that is being published in the dashboard. Here we also need to fine-tune our alert system. So this alert system cron job, let me just call this as a cron job. This cron job is periodically querying this query service based on the defined rules here. So this can query the query service. How does this rule would be defined? We would need the database for storing all those rules. So let's introduce a relational DB here, which is a rules database. This cron job is periodically querying this rule database to load the rules, and based on the rules it will query the query service, and if any threshold reached which are defined in this rules database, then this can send the notifications like email, SMS to the different stakeholders. How does these rules would be defined? So we need one alert and rule service here as well. So I'm calling this as, in fact, what we can do is, so we can define these rules from the dashboard as well. This dashboard can query to this query service to load the data. At the same time, we can also create or define the rules. So let me change this to alert DB, and from this dashboard we can define the rules in this alert DB. For example, if the CPU utilization is reached above 90%, then this cron job will periodically query this alert DB and send the notification so that the stakeholders can take an action on it to scale up or scale down the servers in this infrastructure. And at this point of time, we have our scalable system for loading the dashboard, alerting, and working the end-to-end functionality. Still, let's try to figure out if there are any further areas of improvement, or rather, you might get a question from the interviewer. Do you see if there are any further improvement areas in your design? So let's revisit each of these steps. These servers are emitting the events and are being published to Kafka, and we have aggregator service. Yeah, this aggregator service can be a Flink service from AWS, which is managed service that can aggregate the data from millisecond to a second to a level of second, and store in this OLAP. But what happen if there are any messages which are missed, or the aggregation result, if the services or some services are down for aggregation, or some messages are missed from this Kafka. So as a backup on this kind of a system where these aggregations are happening at the real time from this Kafka messages, we also need to think about the reconciliation process. So we can introduce the reconciliation service. Periodically get the data from S3 bucket and do a kind of a reconciliation on back to this OLAP database. So any information or aggregation result which has missed some messages as part of aggregation real-time process, this reconciliation service will make sure and it will be the true source. Basically, it will override those aggregated results periodically. So we have all the data available in a form of a raw data. This service will fetch these data, do the aggregation and save back to this OLAP DB. What kind of a reconciliation service is this? This is something like a map reducer. Let me mention here, map reducer, which can scale on its own to do this reconciliation. So we have the reconciliation process as well in our system. Let's check all the functionalities are satisfying, or have we missed any of the core functionality. Collect the database, store information, dashboard, rules, creating the rules, availability, aggregations, and this is a schema how we are aggregating in our. And yeah, coming back to this API, so now you see that you have started with one API, but for creating the rules you need more APIs. But I feel, considering the time what you have in your interview, it's okay to start with one or two APIs and then get into the high level system design and propose the end-to-end solution, how is it working, and then get deep dive and keep identifying the bottlenecks and the improvement areas into a system, and ultimately coming to the working solution for a scalable system. I hope you have learned something today. How we started with noting down the core functionalities and what are the quality of the system we need as part of the non-functional requirement, what are the data we need into our system and how we expose those data, and how we start scaling the system from a basic end-to-end high-level data flow to aggregating, to decoupling these instances, to decoupling this component by leveraging the message broker like a Kafka into our system, how we aggregated these data to not to save all this information so that it would be an overburden for a query service to query into this OLAP database, and how we are storing the raw data into the cheap storage, and we also introduce the reconciliation process, and at the end connecting with the end users on the dashboard, how it will query to load these information in the dashboard, and at the same time creating the alerts and running the cron job to send the notifications at the time of any threshold reached based on the defined rule into this alert DB. Please like and subscribe to my channel, which motivates me to create more such videos, and do check out my other system design interviews in the playlist. Enjoy learning. Thank you. Bye bye.